Hello everybody, this is Homer White back again with the 11th chapter of our book. This is on chi-square tests for goodness of fit. In this part, we'll look at an initial example about a question as to whether or not a certain die is fair. This involves the issue of data snooping and how to get around it. And we'll also see a new version of the same old chi-square test to apply to situations of this nature. Always remember to make sure the necessary packages are loaded. So let's talk about the fair die problem. Suppose that you are the sheriff of a rough town in the wild, wild west, and a gambler comes to town. He claims that the die that he plays with is fair, but the locals in the saloon who are playing with him are losing a good bit, and they grumble and mumble that it's weighted in one way or another. So you go to the gambler and you impound his die, and you're going to check it out. You're about to bust it open to see if it's weighted in one particular direction. But the gambler says that it's his lucky die, and he begs you, please don't damage it. So instead, you roll it a certain number of times, let's say 60 times. And let's say this is what you got. Your observed counts are that you got the 1 spot 8 times, the 2 spot 18 times, the 3 spot 11 times, and so on. These observed counts add up to the 60 rolls. Now let's think about what we would expect if the die were fair. If the die were fair, each of the 6 sides would have the same chance, 1 out of 6, of coming up. 1/6 of 60 is 10. So you would expect a count of about 10 in each one of those cells, give or take some, of course, for chance error in the rolling process. Your attention is immediately drawn to the observed count of 2 spots. There's 18 of them, 8 more than what you would expect if the die were fair. That's a lot of 2 spots. So you figure you better run a test on this. So you define P to be the chance of landing with a 2 spot side up. This is going to be a 1 proportion test. Your hypotheses are, null hypothesis is that P is 1/6. That's if this is a fair die. On the other hand, if this is not a fair die, then P would be not 1/6. It would be weighted in one way or another. We know how to do a test on 1 proportion, binom test GC. We have 18 successes in 60 trials. We're counting a 2 as a success. The null hypothesis thinks that the chance of a 2 is 1 out of 6. We're ready to go. If you ran that code and looked in the console, then you found amongst the output that the p-value was about 0.0089. Remember how we interpret that. If the die is fair, then there's only about a 0.89% chance of getting as far from the expected number of 2 spots as we actually got. We'd better reject that null hypothesis, so the conclusion might be a violent one. As sheriff, we might ride the gambler out of town on a rail. But you really need to hold your horses here. We've designed the test of significance based upon observing a large number of 2 spots in the data. We designed the test specifically around an observation that we saw in the data. We didn't have that particular test about whether or not the probability of 2 is 1/6 until we saw that data. We have committed data snooping. We really need a way to take all of the data into account, even-handedly. The chi-square statistic from earlier chapters comes to our rescue here. It has a built-in way of taking all of the data into account. Remember that for all of the cells in a table of results, it will compute the observed count of the results minus what would be expected if the null were correct, square that result, and divide by the expected count. The fact that it does this for all of the cells before summing up the results shows that it takes all of the data into account in an even-handed way. So let's just compute the chi-square statistic for our data in our 60 rolls. There are 6 terms. The sum of them is 8.8. So we wonder, what's the chances that chi-square would turn out to be 8.8 or more if the die is actually fair? Well, you need a p-value here. we could approximate the p-value through simulation. What we need to do is create an R object that gives us the observed counts. We'll call that object throws, and it's going to be a list of the observed counts constructed by the concatenation function. Notice that the observed counts are included, and a nice touch is that you can actually give each of the elements a name using 1 equals, 2 equals, and so on as your desired names. You can use any names you like, but these names seem very nice. We also need to construct an object that says what the null hypothesis thinks the chance of each of the possible sides is. The rep function comes to our aid here. It repeats 1/6 6 times. So null probs is going to be a list of 6 1/6s put together. We have an app to do the simulation. It's called slow goodness. All you have to do is feed it the observed counts, throws, and the null probabilities. Let's give it a try. We're going to need to run this code, and then we're going to need to run this code so that slow goodness will know what throws and null probs are. Okay, if you've run that code, then in the plot window, you should see a bar graph representing the observed counts for the 60 rolls. Over in the console, you see a prompt to begin simulations. For a quick resampling, the machine is going to pretend to roll a die 60 times. The chance of each of the sides of the die is specified by that list null probs, and so it's going to be a fair die, 1/6 chance for each side. After the machine does its 60 rolls, it's going to compute the chi-square statistic for the observed counts that it gets. Eventually, it'll make a histogram of all the chi-square statistics that it gets. This histogram will give us a good sense of the probability distribution of the chi-square statistic in the event that the die really is fair. Let's give it a try. For each set of 60 rolls, all we have to do is press enter. Notice what's happening. At each stage, we have a set of observed counts based on the 60 rolls that we tried from this hypothetically fair die. The chi-square statistic has been computed each time. The machine is also keeping track of how many times the chi-square statistic has gone above the observed chi-square statistic in our study, the 8.8 value. Looking over into the plot window, we see the histogram beginning to take shape. This is a histogram of those resampled chi-square values. We've done 4 of them so far. The most recent one is in red. Let's continue. Notice that sometimes we are exceeding 8.8. I'm probably going to keep at this for a while, so if you like, you could go chill out somewhere. All right, we're back. In the plot window, you see a histogram taking shape. This histogram is our estimate of the probability distribution of the chi-square statistic if the null hypothesis of a fair die is true. Notice there appears to be a somewhat right-skewed distribution here, and a fair percentage of the time, the chi-square statistic will be above 8.8. Looking over into the console, we see that a record has been kept of everything. And we've done 100 resamples so far, and 15% of the time, the chi-square statistic has exceeded the observed value in our study, the 8.8. Let's quit now. So our estimate based on the simulations for the p-value is about 15%. If the die is fair, we're estimating there's about a 15% chance of getting an 8.8 or more when we roll the die 60 times. This doesn't seem so terribly unlikely after all, so maybe we should not jump to the conclusion that the gambler is playing with a loaded die. Now we will look at the whole process a little bit more formally with a new version of the chi-square test. Let's lead off with a little bit of statistical theory. Statisticians have actually discovered a family of random variables called the chi-square family. Just as there is a family of normal random variables and a family of t random variables, so there is a family of so-called chi-square random variables. There's a different chi-square random variable for each number called a degree of freedom. Degree of freedom numbers can be 1, 2, 3, 4, and any higher whole numbers. Here's an example of a density curve for the chi-square random variable that has 3 degrees of freedom. So this is one member of the chi-square family. The density curve is pretty right-skewed. All chi-square density curves for all degrees of freedom are right-skewed, but the right skewness is most prominent at lower degrees of freedom. Statisticians have found out a couple of other things too. Since chi-square random variables are random variables, they have expected values and standard deviations. And it turns out that for a chi-square random variable with a particular degrees of freedom, the expected value is exactly that degree of freedom. The standard deviation for such a chi-square random variable is the square root of twice the degrees of freedom. The notation looks pretty technical, but it comes down to this. If you're working with a chi-square random variable with a certain number of degrees of freedom, then you can expect it to work out to be about the degrees of freedom on average, give or take the square root of twice the degrees of freedom, or so. Statisticians have also discovered some things about the chi-square statistic itself. The chi-square statistic is a random variable because it's based on those observed counts. Those observed counts are based on chance. As a random variable, the chi-square statistic has a certain kind of distribution. It turns out that if the expected cell counts, according to the null hypothesis, are big enough, and 5 or more is usually considered plenty big enough, then as a random variable, the chi-square statistic is distributed approximately like one of the members of that family of chi-square random variables. In particular, it's distributed like the one with degrees of freedom equal to the number of cells in the table minus 1. So for the die study here, our observed counts came in a table consisting of 6 cells because the factor variable side that lands up has 6 possible values: 1 spot, 2 spot, 3 spots, 4 spots, 5 spots, 6 spots. As for the counts expected by the null hypothesis, they're all 10. So they're all above 5. So we know that the chi-square statistic as a random variable has approximately a chi-square distribution, where the degrees of freedom is 1 less than the number of cells that go with our factor variable. There were 6 cells, 6 minus 1 is 5, so we know that our chi-square statistic is distributed approximately like a chi-square random variable with 5 degrees of freedom. Now let's think about expected value and standard deviation. We now know that if the die is fair, then you could expect that the chi-square statistic should work out to be around 5, give or take the square root of 2 times 5. That's about 3.16. So if the die is fair, we're expecting the chi-square statistic would have come out to be about 5, give or take 3 or so. We actually got that chi-square was 8.8. This really isn't so far above what we expected. The p-value, which is the chance of getting at least 8.8 if the die is fair, could be found in other ways than just by simulation. We could use that chi-square curve with 5 degrees of freedom to approximate the p-value for our study. Here's a picture of the density curve for a chi-square random variable with 5 degrees of freedom. Remember, This density curve is a pretty good approximation for the actual probability distribution of our chi-square statistic if the null hypothesis of a fair die is correct. Therefore, the p-value for our test, the probability that the chi-square statistic is at least 8.8, should be approximately the area underneath this chi-square curve past 8.8, the shaded area that you see here. That shaded area is about 0.1173. So our approximation for the p-value is that it's about 11.73%. We really do need to revise our results here. We need to move away from testing just on the 2's, that was data snooping, and we need to use the chi-square test instead. The chi-square test had a much higher p-value, about 11%. It's certainly higher than our usual cutoff of 5%, so we're not going to reject the gambler's claim that the die is fair. Our results were somewhat unlikely. There's about an 11% chance of getting 8.8 or higher if the null is true, but they're not terribly unlikely. This time the 60 rolls did not provide strong evidence that the die is weighted. We might want to keep an eye on that gambler. We might in particular want to keep an eye on the 2 spots in the future, but we really do need new and additional data before we can pick up on any loadedness of that die. Let's go through the whole procedure again, a little bit more formally. So, the chi-square test for goodness of fit addresses the inferential aspect of research questions about a single factor variable. In particular, they answer questions like this one. Does the data provide strong evidence against a claim that the distribution of the factor variable is a particular set of values, a particular set of percentages? So in this die study, when we begin the first step of a test of significance, we always define parameters and we state hypotheses. The defining of parameters here will involve the definition of 6 parameters. That's because there's 6 possible values of the factor variable, what side lands up. And so we define P1 equal to the probability that the die lands with 1 spot up. P2 is the probability that the die lands with the 2 spot up, all the way on down to P6, the probability that the die lands with the 6 spot up. 6 parameters under question. Nobody really knows what the real probabilities are. The null hypothesis in this situation is that all 6 of these probabilities are 1/6. In general chi-square tests, I should note, the null hypothesis doesn't have to say that all of the probabilities are equal. It could be a claim of any sort about the probabilities as long as the probabilities add up to 1. But in this case, where the gambler's claim is that his die is fair, the right way to cast the null hypothesis is that all 6 of those probabilities are 1 in 6. The claim that the die is weighted is simply a claim that at least one of these probabilities is not 1/6. When we do a chi-square test, we have code for it in the chi-square test GC function. That function is going to need the same sort of information that our simulation function needed. It's going to need the observed counts, and it's going to need a statement about what the null hypothesis thinks the probabilities are. So we need to make sure that we've constructed the observed counts and called them something descriptive, perhaps throws. And we need to make sure that we've constructed the null probabilities. Again, the rep function is useful here. We can use any name that we like, but this name, null probs, seems good and descriptive. The syntax for the chi-square GC function is simply to put in the observed counts, and then, using an argument p, set p equal to the null probs. If you'd like a graph of the p-value, you can also set the argument graph to true. Here's a little tour of the results. The output starts with a statement of the observed counts. Also, the function takes the null probabilities, takes into account how many rolls there were, and computes the expected counts for each cell. That's where it gets the column called expected. It then begins to compute the chi-square statistic. So for every cell, it takes the observed, minus the expected, squares that result, divides by the expected value of 10, and gets a little fraction. That fraction is the contribution from that cell to the chi-square statistic. Notice that the biggest contribution came from the cell where the observed difference was biggest. The two spots really did stand out in our study, producing the largest contribution. The chi-square statistic itself is the sum of those 6 contributions. And so the chi-square statistic turned out to be 8.8. The degrees of freedom for the table is 5. That's the 6 possible outcomes minus 1. And the p-value, as we saw, was 0.1173. So we can construct a formal test of significance using the chi-square test GC function. If you would ever like that function to deliver less output, say you just need the p-value, and you don't need a table of observed and expected counts and contributions, then there's an argument called verbose, and you can simply set it to false, as in this code at the bottom. Let's try another example. Consider the following research question. At Georgetown College, are students equally split between front sitters, middle sitters, and back sitters? This time, the variable we're investigating is the factor variable seat from the Math 111 survey data frame. Remember, the possible values of that variable are that a person might prefer the front, the middle, or the back. So we're going to need to define 3 parameters here. This time, the parameters won't be probabilities. We're not dealing with the dice being rolled. The parameters will be population proportions, because the students are a random sample from the Georgetown College population. So let's define P sub F to be the proportion of all Georgetown College students who prefer the front. P sub M shall be the proportion who prefer the middle, and P sub B the proportion of all Georgetown College students who prefer the back. Again, since we don't have access to the entire population, we don't know the value of any of these 3 proportions. But the hypotheses have opinions about them. The null hypothesis in this case is that all 3 of these proportions are 1 divided by 3. On the other hand, if you think that people are not equally split in their preferences between the 3 possible seating positions, then you would think that at least one of these proportions is not 1/3, and you would be a supporter of the alternative hypothesis. The code for the test can use formula data input if you like. So we have one factor variable in consideration. We just need a twiddles in front of it to signal the presence of a formula. The data frame is Math 111 survey. That's where the seat variable is housed. We need to deal with the p argument, which sets what the null hypothesis believes about the population proportions are. Since the null believes that each of them is 1/3, we provide a list of 3 1/3, and perhaps we would like a graph. Here's a little tour of the results. We get the observed counts for people in the survey who preferred the front, the middle, and the back. If in the population the 3 proportions are each 1/3, then you would expect about 1/3 of the 71 students to express a preference for each of these 3 possible positions. 1/3 of 71 is 23.67, and that's why each of these expected counts is 23.67. Working with the observed and expected counts, you can compute the contributions to the chi-square statistic. The chi-square statistic turns out to be about 9.15. What are the degrees of freedom for the table? This time the table is just for the one factor variable. It's these 3 observed counts. There are 3 cells in the table. 3 minus 1 is 2. So if the null is right, we would expect that the chi-square statistic would work out to be 2, give or take some for chance error. The chances that it works out to 9.15 or more are pretty small, only about 1%. That's what the p-value is. Since the p-value is so small, we're going to reject the null hypothesis. Apparently, this data provided strong evidence that the student body is not equally split as far as seating preference is concerned. To close, I'd like to note that if you do want to simulate your p-values, you can always do so. You don't have to do it only when the expected cell counts fall below 5. You can do it anytime you like. It's a good idea to set a seed when you plan to do anything random. And then when you apply the chi-square test GC, provide all of the usual information, but set the argument simulate.pvalue to true. Unlike the chi-square test for relationship between two-factor variables, there's really only one way to do simulation, and it uses the true value for this argument. Remember that you should simulate if one or more of the expected cell counts turns out to be less than 5. Thank you for listening.